Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling Chapter 11 for our MCAT General Chemistry playlist. This chapter is titled Oxidation Reduction Reactions, and we're going to focus on two main objectives here. The first objective is titled Oxidation Reduction Reactions. We're going to begin by defining oxidation and reduction. Then we're going to learn how to assign oxidation numbers to various elements in chemical compounds. And finally, we're going to explore the methods for balancing oxidation reduction reactions. Then the second objective is titled Net Ionic Equations. We're going to start with an overview of net ionic equations, and then following this, we're going to discuss disproportionation reactions. This is a special type of redox reaction where a single substance undergoes both oxidation and reduction simultaneously. Lastly, we're going to briefly cover oxidation reduction titrations. This is a quantitative analytical technique that's used to determine the concentration of an unknown solution by using a redox reaction. With that introduction, let's go ahead and get started with the first objective. Reactions that involve the transfer of electrons from one chemical species to another are classified as oxidation reduction reactions, also known as redox reactions. At their core, these reactions embody the principle of the conservation of charge, which states that electrical charge can neither be created nor destroyed. This fundamental law means that an electron lost by one species must be gained by another, ensuring that oxidation and reduction occur simultaneously. Now, oxidation is defined as the process of losing electrons, while reduction is the process of gaining electrons. These two processes are intrinsically linked. Oxidation cannot happen without reduction because the electron that's lost by one substance has to be gained by another. Now, a useful mnemonic to remember these processes is Leo the lion goes grr. Leo, losing electrons, is oxidation. Grr, gaining electrons, is reduction. Another mnemonic is oil rig. This is my favorite. Oil, oxidation is loss of electrons. Rig, reduction is gain of electrons. Now, in every redox reaction, there are substances known as oxidizing agents and reducing agents. The oxidizing agent is the substance that causes another substance to lose electrons and be oxidized. In doing so, the oxidizing agent itself is reduced as it gains those electrons. On the other hand, the reducing agent is the substance that causes another to gain electrons and be reduced. And so the reducing agent itself is oxidized as it loses electrons. So for example, let's consider the reaction between magnesium and hydrochloric acid. So this is the balanced chemical equation. You have magnesium plus 2 hydrochloric acid molecules. They react to give us magnesium chloride and hydrogen gas. In this reaction, magnesium loses electrons and is oxidized. All right, we go from magnesium to magnesium 2 plus 2 electrons. At the same time, the hydrogen ions from hydrochloric acid, they're going to gain electrons and they become reduced. So we go from 2H plus those 2 electrons they gain to form hydrogen gas. So here, magnesium acts as a reducing agent because it donates electrons and it undergoes oxidation. On the other hand, the hydrogen ions, they act as oxidizing agents because they accept electrons and they undergo reduction. Now, being familiar with common oxidizing and reducing agents can significantly streamline your problem-solving process, especially in organic chemistry reactions. So on exams like the MCAT, recognizing these agents quickly can be a time saver. So let's delve into the specifics provided in this table and understand the characteristics and roles of these agents. Oxidizing agents are substances that gain electrons in a chemical reaction, and in the process they cause another substance to be oxidized. These agents are often characterized by the presence of oxygen or another strong electronegative element such as a halogen. Here are some common oxidizing agents. Here we have oxygen, hydrogen peroxide, the halogens, these are highly electronegative elements that readily accept electrons. We also have sulfuric acid, nitric acid, and sodium hypochlorite. Sodium hypochlorite is commonly found actually in household bleach. We also have potassium permanganate. This is a very versatile oxidizing agent that's used in both the laboratory setting and in industry. You're going to encounter this a lot in organic chemistry. We also have chromium trioxide and sodium dichromate. These are powerful oxidizing agents used in organic synthesis. We also have PCC. This is pyridinium chlorochromate. This is used specifically for the oxidation of alcohols to aldehydes and ketones. And last, we have NAD+ and FADH. These are coenzymes involved in redox reactions in biochemical processes. They act as electron carriers. Now, reducing agents, on the other hand, they donate electrons in chemical reactions and they cause another substance to be reduced. These agents typically contain metal ions or hydride. Here are some common reducing agents. Here we have carbon monoxide and carbon. Carbon acts as a reducing agent in the reduction of metal oxides in a lot of high temperature reactions. Here we have diborane. We also have tin 2 ion and other pure metals. These are commonly used in redox reactions. We also have hydrazine, zinc amalgam, and Lindlar's catalyst. In addition, we have sodium borohydride. This is widely used in the reduction of carbonyl compounds. Also, lithium aluminum hydride. This is a very strong reducing agent that's used in the reduction of esters, carboxylic acids, and other functional groups. And then last, we have NADH and FADH2. These are biochemical reducing agents that act as electron carriers in cellular respiration and other metabolic processes. Now, as a fun fact, biochemical redox reagents such as NAD+, they play crucial roles in metabolic pathways by acting as both oxidizing and reducing agents. NAD+ accepts electrons during catabolic processes, becoming reduced to NADH, which stores energy. During anabolic processes, NADH donates electrons and becomes oxidized back to NAD+, thus releasing the stored energy to drive biosynthesis. This cyclical transformation allows NAD+ to mediate energy transfer within cells, and it facilitates both energy release from food molecules and energy utilization in building cellular components. This dual role is essential for maintaining the flow of energy through metabolic pathways. Now, the next thing that we want to talk about is oxidation numbers and assigning oxidation numbers. An oxidation state is a bookkeeping technique for keeping track of electrons. It treats all of an atom's bonds as if they were ionic, assigning the electrons in each bond to the more electronegative element. It is important, of course, to know which atom is oxidized and which atom is reduced. Oxidation numbers are assigned to atoms in order to keep track of the redistribution of electrons during chemical reactions. Based on the oxidation numbers of the reactants and products, it is possible to determine how many electrons are gained or lost by each atom. So understanding how to assign oxidation numbers is crucial for tracking the transfer of electrons in redox reactions. So we're going to go over a couple of rules that is going to help us assign oxidation numbers to atoms in compounds. The first rule is that the oxidation state of an element in its neutral elemental form is 0. This rule applies because atoms in their elemental form have not gained or lost electrons. So for example, if we look at helium, it's going to have an oxidation number of 0. If we look at diatomic nitrogen, each nitrogen atom is going to have an oxidation number of 0. The second rule is that the oxidation state of a monatomic ion is the same as its ionic charge. This means that the oxidation state directly corresponds to the ion's charge. For example, if you look at sodium ion, it's going to have an oxidation number of +1 since it's lost 1 electron. If we look at a chloride ion, it's going to have an oxidation number of -1 because it has gained an electron. The third rule is that in binary compounds, the element with the greater electronegativity is assigned the negative oxidation state that is equal to the charge it would have if it were a monatomic ion. So if we look at something like sodium chloride, we're going to look at the most electronegative element. That's going to be chlorine here. All right, and we're going to assign it an oxidation number that's equal to the charge it would be if it were a monatomic ion, if it were chloride ion. So it will have an oxidation number of -1. Now, there's a lot that goes in here that we can discuss about different kinds of groups or elements and what their typical oxidation numbers will be in compounds. We're going to discuss that shortly. But let me just talk about the last and final rule, which says that the sum of the oxidation states of every atom equals the overall charge of the substance. So the sum of the oxidation numbers of all the atoms present in a neutral compound is 0. The sum of the oxidation numbers of the atoms present in a polyatomic ion, that's going to be equal to the charge of the ion. So for example, if you're looking at a sulfate ion, the sum of the oxidation numbers has to sum up to be -2 to match the charge of the ion. Now, like I said, for Rule 3 and for Rule 4, what's going to help us is understanding some general trends for oxidation numbers for certain elements in a compound. So we're going to scroll down here and look at our periodic table, and I'm going to go over a couple of things. The first thing that I want to go over is that the oxidation number of alkali metals, all right, for alkali metals in a compound is always going to be +1. This is because alkali metals tend to lose 1 electron to achieve a stable electronic configuration. So let's go ahead and look at our example for sodium chloride again. We said we traditionally look at our most electronegative element first and give it the oxidation number that it would have if it were a monatomic ion. So it gets a -1 charge. Now sodium Sodium is an alkali metal. It's going to have an oxidation state of +1. And we know that we did this correctly because the sum of the oxidation numbers of all the atoms present in a neutral compound is 0. And +1 minus 1 sums up to 0. Now, also another example that we can look at is for lithium chloride. Same thing goes here, all right? What is going to be the most electronegative element? It's going to be chlorine. We're going to give it an oxidation number as if it were a monatomic ion, as if it were the chloride ion. So it gets an oxidation number of -1. Lithium is an alkali metal. Alkali metals have an oxidation state of +1. And again, we know we did this correctly because the sum of the oxidation numbers of all the atoms present in a neutral compound should add up to 0, and it does. Now, a second thing to keep in mind is that the oxidation number for alkaline earth metals in a compound is always +2. These metals typically lose 2 electrons to form stable cations. So for example, in calcium chloride, calcium has an oxidation state of +2. For chlorine, all right, this is going to be -1, and there's 2 of them, so that gives us a total of -2. +2 minus 2 gives us a total of 0. And remember that the sum of the oxidation numbers of all atoms present in this neutral compound of calcium chloride should be 0, and it is 0. So that's how we know we assigned these oxidation numbers appropriately. Now, the oxidation number of halogen elements in a compound is usually -1, except when they're combined with an element of higher electronegativity. So halogens, they typically gain 1 electron to form stable anions. So for example, if we're looking at hydrogen chloride, the chlorine has an oxidation number of -1. All right. However, if we look at something else like hypochlorous acid, HOCl, chlorine is bonded to oxygen. Oxygen is more electronegative. So chlorine will actually here have an oxidation number of +1. Okay, so that's for halogen atoms. Keep that in mind. Something else, hydrogen. The oxidation number of hydrogen is usually +1. All right. However, when hydrogen is bonded to metals in metal hydrides, its oxidation number is actually going to be -1 because it acts as the more electronegative atom. What's an example of this, you ask? Sodium hydride is a great example. Here, sodium is an alkali metal. Alkali metals always have an oxidation state of +1. All right, of +1. So here, hydrogen will actually have a charge of -1. And the way that you know you did this correctly is, again, remember our last and final rule we covered, the sum of the oxidation numbers of all the atoms present in a neutral compound sums up to 0. What about oxygen? Oxygen is a fun thing to talk about. The oxidation number of oxygen is -2. Because oxygen typically gains 2 electrons to complete its valence shell. For example, in water, H2O. This oxygen atom, all right, in water is going to have an oxidation state of -2. Hydrogen has a oxidation state of +1, and there's 2 of them. So that gives us a total of +2. +2 minus 2, 0. That's exactly what we want for this neutral compound. Now, there are exceptions for oxygen that is really important for us to talk about. For example, in peroxides, H2O2, each oxygen atom actually has an oxidation number of -1. This is because in this molecule, we have an oxygen-oxygen single bond. All right, and in this oxygen-oxygen single bond, the electrons are shared equally. Another exception to keep in mind in compounds like oxygen difluoride, OF 2. Oxygen is actually bonded to fluorine, which is more electronegative. So here, fluorine is going to have the negative oxidation state of -1, and there's 2 of them, so that gives us -2. Here, oxygen's oxidation state is actually going to be +2. All right, so those are the rules that we need to keep in mind for the MCAT. Again, I want to repeat that last and final rule because it really helps us with a lot of the problems we're going to be asked in the MCAT and a lot of the problems we're going to tackle in our problem set. That rule is that the sum of the oxidation numbers of all the atoms present in a neutral compound is 0, and the sum of the oxidation numbers of the atoms present in a polyatomic ion is equal to the charge of the ion. And I know I repeated that a lot of times, but repetition is key. That is a really important rule I want you to keep in mind. Now, what we want to do next is tackle an example problem. This example says, assign oxidation numbers to the atoms in the following reaction to determine the oxidizing and reducing agents. Now, just looking at this reaction, all of these species are neutral, so the oxidation numbers of each compound must add up to 0. Here we have tin 2 chloride reacts with lead 4 chloride to form tin 4 chloride and lead 2 chloride. Let's start off with our first reactant, tin 2 chloride. Now, looking at this binary compound, we need to remember Rule 3. In binary compounds, the element with the greater electronegativity is assigned a negative oxidation state that's equal to the charge it would have if it were a monatomic ion. So here, chlorine is obviously more electronegative. So we're going to assign it a negative oxidation state that's equal to the charge it would have if it were chloride ion. So we're going to assign it a -1 charge. Now there's 2 of them, so we have to multiply this by 2. We get a total of -2 charge for Cl2. Now, this is a neutral compound, so tin is going to have an oxidation state of +2 to ensure that when you add up the oxidation numbers here, they add up to 0 because this is a neutral compound. Again, in this tin 2 chloride, tin has an oxidation number of +2 because there are 2 chlorines present and each chlorine atom has an oxidation number of -1. Similarly, we can look at tin 4 chloride here. Okay, we have 4 chlorine atoms. Each has a -1 oxidation number. For all 4 of these, this gives us a total of -4. That means tin in this compound is going to have an oxidation number of +4. Wonderful. Let's go ahead and look at lead 4 chloride. Here, again, chlorine atoms are the most electronegative. We're going to assign it a -1 oxidation number. There's 4 chlorine atoms for a total of -4. That means that lead here is going to have an oxidation number of +4 to ensure that for this neutral compound, the sum of the oxidation numbers adds up to 0. Similarly, we can do this for lead 2 chloride. Again, chlorine is the most electronegative atom here. We're going to assign it a -1 charge. There's 2 of them. That gives us a total of -2. That means that lead in this compound is going to have an oxidation number of +2. Okay, now the oxidation number of tin, it goes from +2 to +4. It loses electrons and thus it's oxidized. It's oxidized, which makes it the reducing agent. Tin is our reducing agent. Now, looking at lead, because the oxidation number of lead goes from +4 to +2, It gains electrons, and so it is reduced, making it the oxidizing agent. The sum of the charges on both sides of this reaction is equal to 0. So we know that charge has been conserved. And so at the end of this, to answer this problem, we want to assign our oxidizing and reducing agents. Tin is our reducing agent. Lead is our oxidizing agent. And with that, we have completed this example problem. And we're actually going to end this first video for this chapter right here. In the next video, we're going to continue Objective 1 and finish Objective 2. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.